Since the dawn of our existence, humans have looked at the world around us and to the sky above us in wonder, wanting to learn and discover. The dream of flight has captured the interest of the world's greatest minds, and many have dedicated their lives to this aspiration, from primitive and deadly forms of biomimetics to the intricate and exacting study and experimentation of mathematical and mechanical concepts. The latter has led to the discovery of laws and equations that govern every corner of the universe, which allowed early pioneers and pathfinders to start developing and testing kites and gliders. On the 17th of December 1903, the first powered and controlled flight was successfully achieved by the Wright brothers. This flight was the spark that lit a fire of groundbreaking aerospace development that continues to burn brightly today. The main force that has allowed all of this to happen is lift. Birds, insects, and the 10,000 plus aircraft in the sky above us right now stay airborne thanks to their wings and the lift that they produce. The Earth's atmosphere consists of countless molecules of oxygen and nitrogen. When they strike the wing of an aircraft, the force is generated perpendicular to the direction of flow, pushing the aircraft upwards, overcoming the force of gravity. The reason why a wing produces lift is because of its cross-sectional shape, which is called an airfoil. Amazingly, despite there being over 300 years of aerodynamic research, scientists and engineers cannot actually agree on what truly allows an airfoil to cause lift. There are two main theories, Bernoulli's theory and Newton's theory. It is worth noting that these two physicists didn't develop the theories, but are named after their laws and principles upon which the theories are based. For us to gain a greater understanding of how air behaves around a wing and how both theories of lift are relevant, I took a trip to Dublin City University's computational fluid dynamics studio. Through multiple previous and ongoing projects, I've gained a lot of experience using ANSYS FLUENT. This is a cutting-edge CFD solver used by many of the world's finest engineers. Using SolidWorks, I've modelled a 2D cross-section of a typical cambered airfoil found on today's airliners, such as a Boeing 787 or an Airbus A350. I ran a steady pressure-based simulation with 500 iterations. Looking at this image here, you can see the air flowing over the wing at 200 meters per second, which would be a slightly low cruising speed for a modern aircraft. The air is flowing smoothly over both surfaces of the wing, which is necessary for lift to be produced. Newton's theory of lift says that lift is caused by the aerodynamic reaction forces acting on the surface of the wing. When air interacts with the wing and is pushed downwards, we can see this happening at the trailing edge of the wing as the streamlines move downwards. Because every action has an equal and opposite reaction, the wing is pushed upwards, thus producing lift. To further verify Newton's third law, I set up a simple experiment. Here's a small DC motor with a 3D printed fan that I designed mounted on it. When I switch on the fan, it'll push air outwards. This action will then cause the system to roll in the opposite direction with equal force. Here is one of the fan blades. If you look at it from this angle, you can see that it is in fact an airfoil, similar to the one used in the previous simulation. As the airfoil rotates with the fan, it pushes air away from it, and the air then pushes the airfoil. The only real difference between what's happened here and what's happened in the wing simulation is that the air is being pushed horizontally and that the wing is moving axially rather than in a straight line. Now that we have demonstrated the theory of lift that involves Newton's third law of motion, we can move on to Daniel Bernoulli's theory. Through a series of experiments in 1738, he concluded that as a fluid increases in velocity, it reduces in pressure, temperature, and potential energy. Here's another screenshot from the simulation shown earlier. This time, contours of flow velocity around the wing are being shown. As air flows beneath the airfoil, it loses velocity but gains potential energy and pressure. The lowest flow speeds are shown within the blue regions. On top of the wing, the exact opposite is happening as air starts to flow faster and lose pressure, highlighted by the red and yellow contours. If we switch the output from velocity to pressure, we get something that looks like the inverse of the previous image. Due to Bernoulli's principle, the low velocity air is now high pressure air, which puts it up against the bottom surface of the wing. The low pressure air above the wing can offer little resistance to this upwards force, and lift is produced as the wing ascends. Mathematically, both theories can contribute to the lift equation, which can be used to calculate the lift that an airfoil produces. I ran a second simulation with ANSYS FLUENT with the same parameters, but this time using an envisaged frictionless theoretical model, which matches the model used by the equation. I then got the lift force created by the wing, which is over 181,000 newtons. If we divide this force by the dynamic pressure of the air, multiplied by the airfoil chord, we get the coefficient of lift, which is 1.153. If we then multiply the lift coefficient by the flow velocity squared and the chord, then divided by 2, we get back the lift force of 181,386 newtons, which was shown in the previous screenshot, proving the accuracy of the simulation. Aside from the shape of the airfoil, another critical factor in the amount of lift that a wing can produce is the angle of attack. The higher the angle is, the higher the lift is generated until a point where flow separation occurs. I ran a third and final simulation, this time with a more traditional airfoil shape and a Reynolds viscosity model, to see what happens when an aircraft wing stalls. Here are the results showing the chaos that is caused when an angle of attack is too steep. This is why if pilots enter or stall, they point the aircraft downwards counterintuitively to stay flying upwards. So the next time you look above your head to see an aircraft racing to its destination, or you are indeed the person on that aircraft, hopefully you can appreciate and contemplate the people and the science behind this incredible feat.